Okay, hi folks. So this is your second video to look at the measurements, observations, and then the essential question that we are going to form from the demonstration. So what you're seeing, this is from the first block, but everything on the board is pretty standard in terms of what we are viewing with the setup, what we can measure, and then what eventually we will use as our essential question. So first thing that I want to, oop, I'm not in the video. Nope, still not. There I am. Okay. So first thing that I want you to note is that, yes, the activity is the modified Atwood Lab, but the learning goal has two pieces to it. So to be able to make conclusions not only about kinematics, but forces as well with 95% accuracy. So looking at that R squared value. But if we're looking at kinematics and forces, we're looking at the how and the why. So when we go to make our essential question, we have to be aware of both of those pieces. So what motion are we viewing, and then why are we viewing that motion? What would those FBDs look like? Okay, so starting with some of the standard observations, and again, this is going to be up on the board for you. I'm also just going to take a picture of it and then put it into a Google Doc. So first thing we know, hey, we're using a frictionless track, but really we're using a whole frictionless system. Next thing, the track was indeed level, meaning that we're dealing with a scenario 1 problem, not a scenario 2, not a scenario 3. We will deal with those, but we kind of have to deal with scenario 1 first. Now, two things is that there were weights or masses that were placed on both the top of the trolley and that was hanging on the string. So kind of two places where we're seeing the masses located. Now, looking at some more measurements. So when the car moved, the weight went down to the floor. So yeah, that was kind of the whole point, is to pull this whole system not only over, but also downward. Again, we are constantly stopping the system the moment before it hits the ground for the purpose of, hey, we're dealing with some type of motion of the system. As soon as we hit the ground, we've taken a piece of the system out. So we really can't continue to look at it when we've changed the setup. Now, after all of that, what we can kind of clearly say is, instead of just saying, oh, the motion of the system, we really are dealing with a uniform acceleration. First thing that gives it away is, hey, you're starting at a velocity of 0, and then it's not 0 anymore, right? It gets faster and faster as it moves down the track. The other thing with that then comes is that the more mass that was actually on the string, or what we call the hanging mass, the faster that final velocity was, and the quicker we got to that final velocity, meaning that the acceleration was increasing as I increased the mass, or it decreased as I decreased the mass. So that's really, we're dealing with uniform acceleration. It's definitely not a constant velocity. And then here is where the why behind the acceleration, oh, because I put more mass on the hanging portion of this system, therefore it went faster. One thing to note is that I did have books underneath my track. Truly, if I were to do the demo again, I'd probably put at least 3 or 4 books just to give myself a little bit more distance to travel. And with that, know again that I did hold your delta, or my delta x constant. I started and stopped at the same points because I do want something to be constant. Actually, I want several things to be constant throughout this setup, and keeping the distance constant is definitely going to make things easier, because then that's one less thing I have to measure. Now, since it's a uniform acceleration, could I change the distance? Sure, I'm still going to get the same acceleration, but time is still changing, acceleration is changing. Why change distance as well to just add another piece that you have to record? So it's definitely easier to just have distance as a constant. Now, the last thing, and this is super important, so I'm going to pull you closer. The total mass of the system was held constant. Because what you saw me do is if I wanted to change my masses, I only interchange the masses within the system. So I simply transferred the mass from either being on the trolley, then to the hanging, or from the hanging back onto the trolley. I didn't bring anything into the system and I didn't take anything out of the system. Because one thing to already recognize is if you take off the trolley, well, now you're changing the mass that's on top of there. You're also changing what's on the hanging, so now that's another place that is changing. If you were to change then the mass of the system as a whole, that would be a third mass that you would change. That's way too many changing variables. This is definitely by far the biggest thing that you have to make sure when you do this lab is that whatever total mass you start with, whatever you have on top of the trolley and you have hanging, you can interchange the masses, but you must keep that total constant. If you don't do this, you will get results that don't make any sense because you have too many changing variables. So that's kind of your big thing. So highlight that, make sure you know it. However, even though you're not changing it, this is still something that you need to record because when we do a whiteboarding discussion, we're going to want to see, hey, if you got different numbers from me, could it potentially be because we had a different total mass? So we want to keep that in mind. All right, so I'm going to move you over to the other part of the board. And looking at what we can measure, obviously, first and foremost, we're going to be able to measure the total mass, time, distance. We could indeed calculate final velocity, but remember that the final velocity equation is Vf is equal to AT plus Vi. So if you want to look at final velocity, fine, but you still need acceleration before you can do that. And then also, yeah, you can measure the hanging mass, but really, this is where that Y piece comes in. Because as we're looking at this, we know that how the system is moving is within an acceleration, right? It has a uniform acceleration. So that's going to be one of our main focal points is the how, but then here's the why. Why is it accelerating and why is that acceleration greater when we have a larger mass? Well, we have a larger force of gravity. And remember, force is that dynamic portion, the why behind the motion. Mass in and of itself doesn't do anything. It just, here's how much matter I have. But when gravity pulls down on it, when you have that Fg is equal to m times g, that is why the system moves at an accelerated rate. So when we look at the essential question, what we're truly looking at is how exactly is the acceleration being affected by that force of gravity of the hanging mass? Is it affected linearly? Is it affected in terms of a top opening, side opening? Do we have a maximum here? And that's really what we need to figure out is what relationship is there between these two things. Now, if you wanted to take it another step and you want to look at final velocity versus hanging mass, go for it. This is your lab, so have at it. But we still need to kind of look at this first as a step one before we can get to this as a step two. But then also remember that in order for you to get acceleration, you still have to know your distance and time, and then use delta x is equal to 1/2 at squared plus vit. So while this is your essential question, and this is what you are graphing, you're still going to need to know this information before you can calculate A. So this will be a couple steps, but ultimately, this essential question is what you graph. If you want to graph the other things, fine, have at it. But this truly is ultimately what you will present during a whiteboarding discussion. Okay, so hopefully that has given you enough to get you started on your lab. As always, if you have any questions, please feel free to email me.